The continuous time Fourier series allows us to express any periodic signal as a weighted sum of cosines and sines, or a weighted sum of complex exponentials. To understand why this is useful, let's first look at this example where we have an LTI system with impulse response h of t and an input to the system which is k1 times e to the power of j omega 1 t. We know that the output y of t is a convolution of h and x, which is the same as the convolution of x and h, and hence can be written as the integral between minus infinity and infinity, h of tau, x of t minus tau, d tau. Replacing h and x gives the integral between minus infinity to infinity, h of tau times k1 e to the j omega 1 times t minus tau d tau. Note that the factor k1 and e to the j omega 1 t is independent of tau. Hence, we can move it outside the integral so that the integral is equal to k1 e to the j omega 1 t times the integral of minus infinity to infinity of h of tau e to the minus j omega 1 tau d tau. When solving this integral, the result will be a complex number that depends on the frequency omega 1. Let's define this complex number as a complex function of omega 1 and express it as h of omega is equal to the integral between minus infinity to infinity of h of tau e to the minus j omega tau d tau, so that we can write that y of t is equal to k1 e to the j omega 1 t times h omega 1. Then we see that when applying an input that's a complex exponential with frequency omega 1, the output is also complex exponential with frequency omega 1, which is multiplied by the complex number h of omega 1. To understand better what this means, let's write the complex number h of omega in its polar form, where we have the magnitude, which we call a, which is a function of omega, and the angle phi, which is also a function of omega. With this reformulation, y of t is equal to k1 e to the j omega 1 t times the magnitude of h of omega 1, which is a of omega 1, times e to the j and the angle for omega 1, which is phi of omega 1. Slightly reorganizing and reordering the term yields that y of t is equal to k1 times a of omega 1 times e to the j of omega 1 t plus phi of omega 1. This shows us that when applying a generic complex exponential as an input, what we get at the output is also complex exponential with the same frequency omega 1. However, the magnitude is scaled by a of omega 1, which is the magnitude of the function h of omega evaluated at the input frequency omega 1, and the output has an additional phase angle phi of omega 1, which is the phase angle of h of omega evaluated at the input frequency omega 1. Using Euler's formula, we can rewrite the input x of t, which is a complex exponential k1 e to the j omega 1 t, as a sum of a cosine term and a sine term. Applying the same trick again to our output signal y of t, which is also complex exponential, but scaled with a of omega 1 and the additional phase shift phi of omega 1, yields k1 a of omega 1 cosine of omega 1 t plus phi of omega 1 plus the sine term j k1 a of omega 1 sine of omega 1 t plus phi of omega 1. This shows that when applying a cosine term to an LTI system, the output is also a cosine term where the magnitude is again scaled with a of omega 1 and the phase is shifted by phi of omega 1. Likewise, when applying a sinusoidal as an input, the output is also a sinusoidal function, with again the magnitude scaled by a of omega 1 and the phase shifted by phi of omega 1, where of course omega 1 is the frequency of the input signal. So this is actually a very important property of LTI systems. So let's repeat again. If we have a system, an LTI system to be precise, represented by this function h of omega, we apply as an input signal a complex exponential or a cosine or a sine with a given frequency, let's call this one here omega 1, then the output will always be a scaled and time-shifted version of this complex exponential, sine, or cosine with the very same frequency. So the scaling is always given by the magnitude of h of omega at this frequency, here omega 1, and the phase shift is always going to be the phase angle of h of omega for omega equals omega 1. So this is a very important and very helpful property, but you might argue that it only applies if we have as an input signal a complex exponential or a single cosine or a single sine. But keep in mind that this h of omega describes an LTI system where L stands for linear. And linear system satisfies the superposition principle. To illustrate what that means, let's assume we have a different input signal now, which is a cosine with frequency omega 1 multiplied by some factor alpha plus a sine of a different frequency, maybe at omega 2, multiplied by some factor beta. Then, by superposition principle, we can get the output of the system. It's going to be alpha times capital A, which is again the magnitude of h of omega, evaluated at omega 1, cosine of omega 1t plus phi of omega 1, plus a scaled and phase-shifted version of the sinusoid, which is beta times a of omega 2 times sine of omega 2t plus phi of omega 2. We can apply the superposition principle not only to sums of two cosines or sines in complex exponential, but to all finite and infinite sums. For example, if you would have an infinite sum indexed with n of complex exponentials scaled with kn and with frequencies omega n, then the output of the LTIC system would be again a sum, an infinite sum indexed with n, kn of a of omega n, e to the j omega n t plus phi evaluated again at omega n. So because the system is linear, we can use the superposition principle. As soon as we have an input signal which is the sum of cosines or sines or complex exponentials, even if the sum is infinite, the result or the output of the system can be obtained very easily simply by scaling and phase shifting the input signal. What the continuous time Fourier series allows us is to basically apply the same trick to any periodic signal x of t. So let's assume that we have a periodic signal x of t with fundamental frequency omega 0. Then by applying the Fourier series, we can express x of t either as a constant plus an infinite sum of cosine and sine terms, where the sine goes from 1 till infinity, and the frequency of the sine and the cosine terms are multiples of the fundamental frequency omega 0, and the cosine terms are scaled with a n's, and the sine terms are scaled with b n's. Or we can also express this periodic signal x of t as an infinite sum, this time the sum going from minus infinity to infinity, of d n's times complex exponentials, which also have frequencies multiples of omega 0. The first way of writing x of t as a weighted sum of cosine and sine terms is called the trigonometric Fourier series. The second expression, which writes x of t as a sum of complex exponentials, is called the exponential Fourier series.